A really good day to IR Dr. Chua Billy. My name is NUR FAEZA FARHANA, and I will present assignment 2 finite element method. There are two tasks in this assignment. The first task is beam analysis by using 4 different type of element, which is the first one is Q4, 2 row, 10 column. The second one is CST, 2 row, 10 column, type 1. The third one is type 2, and the fourth one is type 3. Figure 1 is a beam dimension and boundary condition, and the beam dimension is for length 0.1 meter, the height is 0.02 meter, the thickness is 0.05 meter. For boundary condition, I fixed at the left side of the beam here, and I apply 2000 Newton force at the top right side here. For material, since it's given Young modulus 200 gigapascal in the question, I assume the material will be carbon steel IC1020. And for the material properties, Poisson ratio will be 0.29, density 7.87 grams centimeter cube, tensile strength is 395 or 395 megapascal, yield strength is 295 megapascal. The first one is classical beam theory, which is calculation. Based on the cross-sectional area of the beam, it is a rectangular shape where the width of the cross-sectional is 0.005 meter. The height is 0.02 meter. So finding the moment of inertia by using formula I equal to BH cubed over 12 and substitute all the value, we will get inertia of 3.33 exponent negative 9 meter square. Maximum stress by using formula, maximum stress equal to MC over I, where M equivalent to force times width length of the beam, and C is the height over 2. So substituting all the value, we will get a maximum stress of 600.006 megapascal. Calculating maximum displacement by using formula FL cubed over 3 EI, where F is force applied, L is the length of the beam, E is the Young modulus, I is the inertia, and we will get maximum displacement of 1.00001 millimeter or 1.00001 exponent negative 3 meter. For the first one, Q4 2 row, 10 column, in terms of displacement, here is the plot of displacement of magnitude. And based on the figure, we can see maximum magnitude of 0.009225 meter. And comparing the simulation value with the classical result, we will get percentage difference of 8.40%. Moving on to the stress, this is the plot of principal stress 1 for the Q4 2 row 10 column, and we get the maximum stress, which is 5.831 exponent 8 or 583.1 megapascal. Comparing the value, we will get percentage difference of 2.90%. For CST 2 row 10 column type 1, here is the plot displacement, and we get a maximum displacement of 0.08505 exponent negative 3 meter, and we will get percentage difference of 1075.79%. For stress, here based on the figure, we get maximum stress 32.9 megapascal, and percentage difference will be 1723.73%. Moving on to the third type element, which is CST 2 row 10 column type 2. In terms of displacement, here is the plot of displacement, and we can see from the figure, maximum displacement is 0.009059 meter, and calculating the percentage difference, the value will be 10.39%. in terms of stress, here is the plot of principal stress 1, and we get the maximum value of stress, which is 573.1 meter pascal, 1 megapascal, and the percentage difference will be 4.69%. The last type will be CST, 2 row 10 column type 3. For the displacement, as shown in figure 8, maximum displacement will be 0.0008821 meter, and percentage difference will be 13.37%. Last but not least is the stress. Plot of principal stress 1 shown in figure 9, and we can see from here, which is the maximum stress is 575.2 megapascal, and the percentage difference between the FEA result and classical result will be 4.31%. So here is the comparisons of result. Table 1 shows the comparisons of result. We can see from table 1, the Q4 2 row 10 column has the smallest percentage difference compared to other types, which is the percentage difference for maximum displacement is 8.40%, and the percentage difference for maximum stress is 2.90%. This is because CST element models produce deeper models than the actual beam's behavior. The deflections are predicted to be smaller than classical beam theory predicts. For the Q4 element model, predicts more accurate deflection behavior than the CST model. And CST model is not able to stimulate the bending behavior nearly as well as Q4 element. That's the reason why the percentage difference for maximum displacement meter and percentage difference for maximum stress of Q4 2 row and 10 column is the smallest. But here we can see in terms of maximum stress for the CST 2 row 10 column, as the type increase, the percentage difference will decrease, meaning the value of the maximum stress become closer to the classical theory value. Moving on to the task 2. Task 2 is beam analysis to find the position that experience higher stress by using symmetry, since the geometry is symmetry. It's actually to simplify the problems and the solution to get the analysis of the beam. And in figure 10, it shows the dimension and boundary condition. And all dimension and boundary condition in figure 10, the unit being changed from inches to meter, where 1 inches equivalent to 0.0254 meter, and the unit of force changed from pound to Newton, where 1 pound equivalent to 4.448 Newton. From here, to find force for the complete model, it will be 200 pound per inches times with the length, which is 2 inches, and we will get 400 pound. But to get only for the symmetrical part or symmetry part, we will divide it into 2, and we will get 100 pound for the force acting on the end of the model. And we transfer or convert 100 pound into Newton, and it will be equivalent to 889.6 Newton. And here is the dimension boundary condition after changing all the unit to SI unit. As we can see, the force applied at the end of the model is 889.6 Newton. And we do an assumption where the thickness of the model will be 2 inches or equivalent to 0.0508 meter. And the material assumed is carbon steel IC1020. So the tensile strength will be 385 megapascal. Yield strength will be 295 megapascal. Young modulus will be 200 gigapascal. Poisson ratio will be 0.29. And last but not least, density will be 7.87 grams centimeter per cube, where the unit will be changed into SI unit later. So here is the plot stress in figure 12. And for the meshing, I am using Q4 to mesh the model, and approaching to end, I want to reduce the number of elements. So to connect a smaller Q4 to the bigger Q4, I am using a transition triangle at this area. So the maximum stress from based on the figure 12, you can see here is 4.445 megapascal. And theoretically, for carbon steel IC1020, the yield strength will be 295 or 295 megapascal. Since the maximum stress obtained from simulation, which is 4.445 megapascal, is lower than the yield strength of the material, which is 295 megapascal, therefore failure will not occur. For a conclusion, based on figure 12, high stress concentration occur at filleting area, which is this area. And irregularities in geometry or materials disturb the flow of stress, where when they are filleting area, the cross-sectional area will be changed. And that's caused the flow stress to be disturbed. And as a result, the concentration stress will occur. An example of irregularities that can cause stress concentration are hole, notch, and fillet. So that's all from me. Thank you.